Welcome back to AlgoJS. Today's question is LeetCode 1469, find all the lonely nodes. So in a binary tree, a lonely node is a node that is the only child of its parent node. The root of the tree is not lonely because it does not have a parent node. So given the root of a binary tree, return an array containing the values of all lonely nodes in the tree. Return the list in any order. So in our first example, we have this binary tree and the only lonely node is 4. And the reason for this is the parent node 2 has only one child, right? 3 cannot be a lonely node because the parent node 1 has both left and right child. In our second example, we have 2 lonely nodes, so 6 and 2, and the reason for this is the parent node only has one child, whereas all other nodes have 2 children. And again, the root is not considered a lonely child because it doesn't have a parent node. So let's dive into the walkthrough. So with this question, there are 2 approaches. We can use BFS or DFS. We will look at both of these today. So with BFS, we're going to be looking level by level to see whether the current node has both children or not. So we start off at this level, we check to see whether it has both children. In this case, 2 and 3 are present. So there's nothing that we need to add into a result array, which we can add down here. Then we go on to the next level. We look at 2 to begin with. 2 has only one child because the left child is pointing to null. So we can add that into our results array. And with 3 is going to be pointing to both null, so it has neither children, so we can forget about that now. And then if we go down to the last level, 4 is pointing to null for both children, so neither child is present, so we can just return this answer now. So the code for the BFS solution is going to look like this. So firstly, we need to make sure that root is available. If it isn't, we can just return an empty array. We have a queue within BFS, which is just a data structure which restricts the process in order to first in, first out. Let's have an answer array. So while there is something within queue, we get the current node, which is equal to queue.shift. And we need to check whether the current left child is available and the current right child is not available. That is one option, in which case we can push into the queue current at left, and we also need to push into the answer array current.left.val. And then we need to check the other side. So if current at right is available, but current at left is not available, then we push into queue the right child, and we need to push into ants current.right.val. And lastly, if both are available, so if the left and right child are both available, so we can add to the queue the left child, and we can add the right child also. And then we can just return the answer array. Okay, great. So that's the BFS solution. Now with DFS, we will be using recursion. So as in any question that uses recursion, we're going to have base cases, and we're also going to have a results array. So our base cases, let's consider a binary tree, or the smallest possible binary tree, where the root is equal to null. What will we return? Well, we can return an empty array, or we can just return nothing, right? So if root is equal to null, just return. So that's the first base case. The second base case is we need to look at the root's left child. So if we're at this position, we need to look at the root's left child and right child. So if the left child is not available, so say this was null, and the right child was available, we need to push into results the right child's value. So if root at left is equal to null and root at right is available, we push into res, so res.push root.right val. And then we need one more base case for the opposite. So if root.right is equal to null and root.left is available, we just push into results the left value. So we do the opposite of this. Okay, so let's run through this. So with depth first search, we go down to depth. So we go down here. This is going to be equal to n. So this is just going to return up nothing. We go down the right side. We have 4. 4 is pointing to no children. So they're just going to return up and then return up from this. We hit 2. So we check this value. We look at its left child, which is equal to null. So this is correct for this base case. We check its right child, which is equal to 4. So there is a value there. So that's correct too. So we just push into res root.right.val, which is this value here. We push that in. We go up to 1. We need to go down the right hand side. 3 doesn't have any children. They're both pointing to null. So we return up from that. And then we get to 1. 1 has 2 children. So these are not lonely. So we can return out of this. We've checked all nodes and res is going to be returned here. So this is going to be our output. So time complexity for this is going to be on because we are traversing the entire binary tree, and space is also going to be on because we're utilizing a stack data structure within this DFS solution. So there's not much code for the DFS solution. We'll initialize our result array. We'll create a function called DFS. So we'll write out the base cases. So if root is equal to null, we just return out of that. If root.left is null and root.right is available, we push into results root.right.val. And then we do the opposite. So if root.right is equal to null, but root.left is available, then we push into results root.left.val. And then we need to start at the bottom. So we go root.left. And then we also need to do root.right. So we are utilizing a post-order traversal here. So it's the left side of the subtree first, then the right side, and then we visit the root. We need to call DFS, and then we can return result. And there you go.